Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about principles of radiation detectors, and in this we are going to discuss about radiation detectors in medical physics. Okay, first of all, why to detect radiation? Why do we need radiation detectors? What's the use of this? Okay, in this lecture video, we are going to discuss about why to detect radiation, interaction of radiation with matter, types of detectors, how to detect radiation, and the applications of radiation detectors. Okay, first of all, what do you mean by radiation? We know that a radiation is the emission or transmission of energy in the form of waves or particles through space or through material medium. Here we have ionizing and non-ionizing depending upon the energy. And what is detection? The action or process of identifying the presence of something concealed. It is called detection. Here we have radiation detectors. Okay, and what are the types of radiation detectors? Already we have discussed, we have both ionizing and non-ionizing. In ionizing we have electromagnetic waves, in this we have x-rays, gamma rays, and also we have particles. Here we have alpha, beta and neutrons. Okay, then why to detect radiation? Actually, we have some applications like research applications, environmental safety, power regulation in nuclear reactors, personal protection of occupational workers, estimation of radiation dose in treatment of patients, calibration of radioactive isotopes, and we have so many applications in radiation detection. Okay, and here we consider the interaction of ionizing radiation with matter. Here we have in the left hand side we have alpha, beta, gamma and neutrons. These are all called particles. And we have interaction of ionizing radiation with matter. In this we have charged particles interaction strongly with ionized directly, and also we have neutral particles interaction less, and these are ionized indirectly and penetrate further. Here we use Bremsstrahlung, mainly we use Bremsstrahlung principle. Okay, here in this detection, the characterization and effects of radiation are almost entirely dependent upon their interaction with matter. Here, this direct ionization charged particles, alpha, beta, and Coulomb interaction with matter, it directly causes ionization and excitation of atoms. In indirect ionizing radiation, neutrons and photons, which have no charge and during interaction with matter, it can transfer energy to charged particles itself. Okay, here in types of detectors we have gas filled detectors, solid state detectors, charged coupled detectors. In this gas filled detector we have ionization chamber, proportional counter and Geiger-Miller counter. And we have solid state detectors. Here we have pin junction, scintillation counter and silicon drift. In charged coupled detectors we have two types, one is direct and another one is indirect we have. Okay, in this ionization chamber, the principle is gas molecules get ionized when energetic charged particles propagated through a gas. Here, this construction, here we have a metallic cylinder filled with a suitable gas at atmospheric pressure, and we have a metal rod fixed along with axis of cylinder, and it is connected to a counter through an amplifier. See this one. Here we have a metallic cylinder, a metal rod and a counter through an amplifier. Okay, and the working of radiation detectors, a suitable potential difference is applied between cylinder and applied electrode. Here, when an energetic charged particle is allowed to enter the cylinder, here the ionization of gas molecules takes place. Here positive and negative ions so created start moving towards oppositely charged electrodes, cylinder and rod. Depending upon the number of particles entering into the cylinder, an electric pulse of proportional magnitude is developed here. This pulse reaches an electronic counter after amplification and number of particles is counted. This is the working principle of counters. And we have two types of ionization chamber. First one is non-integrating type ionization chamber. Second one is integrating type. And this non-integrating, the type of gas is so chosen that the response time of gas is small relative to the frequency of the entering particle. Here, the different pulses are recorded for each particle entering into the cylindrical chamber. In this integrating type, the type of gases, the response time of gas is large relative to the frequency of the entering particles. The pulse showing ionization by each particle is not recorded separately, but a continuous flow of current is recorded here. The quantity measured is not the number of particles, but the total ionization charge accumulated on the electrode is considered here. See this one, here we have proportional counter. Here the gas molecules get ionized when energetic charged particles propagated through gas. Here we have a cylindrical tube, it containing a mixture of methane and argon, and we have a fine tungsten wire fixed along with the axis of the tube. Also we have an amplifier and discriminator. See this one. Here we have a cylindrical tube. Okay, and we have a tungsten wire. We have amplifier, discriminator, and again we have amplifier in the output stage. Here the working is, when an energetic charged particle enters into the cylindrical tube, it ionizes the gas molecule colliding with the particle. The ions so produced get accelerated due to high potential difference between electrodes and cause further ionization of gas molecules. Here, the total number of ion pairs created by a single primary ion is called multiplication factor of the gas. Here, the charge accumulated on the electrodes give rise to an electric pulse that is fed to the discriminator that is cut off low voltage undesired noise pulses. Okay, here see this one, the range of voltage within which counting the rate remains constant is called Plateau region. Here we have counting rate and voltage as x and y axis. Here we have Geiger-Miller counter, GM counter. Here the principle is gas molecules get ionized when energetic charged particles propagate through a gas. Same, the electrons produced by ionization, if accelerated by a high potential, can cause further ionization of gas molecules, thereby generating a large number of more electrons here. See here the construction. Here we have input particles like alpha, beta, neutron. We have glass tube, and inside we have copper tube, and we have tungsten wire. We have amplifier and counter for radiation counting purpose. See this one. Here the working is, when an energetic charged particle enters GM tube through the window, the gas molecules which interact with the charged particle get ionized first. The generated electrons get accelerated towards the central anode and positive ions towards cathode tube. The accelerated electrons cause ionization of more gas molecules, generating large number of electrons within a very short interval of time called avalanche effect. The avalanche gives rise to high current pulse. For each particle entering the tube, successive current pulses are produced and counting is done by a suitable device. Here we have dead time of GM counter. Here we have T equal to 1 by n minus 1 by capital N. So here T equal to n minus n by n multiplied with caps N. Here capital N is particle enter the tube per second, and the counter shows small n particles per second. So the dead time is T equal to n particles enter the tube minus counter shows n particle per second. So n minus n by small n multiplied with capital N. Okay, and we have quenching of GM tube. Here many methods have been suggested for quenching, but the most acceptable method is self-quenching method. Here, in this, electrons are created neutralize the already existing inert gas positive ions, and the negative halogen gas ions get very rapidly drifted towards the surface of the cathode tube, where they get neutralized here. Here we have how to detect radiation. See this one. Here we have a practical example. Here choose a radiation detector working on a particular principle of interaction, either ionization, scintillation, or counting over the known sensitivity to estimate the radiation under detection. See this one. Here we are using a 451P ion chamber survey meter to detect X-ray scattered radiation. It is designed to measure gamma and X-ray radiation above 25 kilo electrovolt and beta radiation above 1 mega electron volt using the latest CMOS and LCD technology. Also, we have some specifications like a radiation detected, operating range, accuracy, detector, and environmental changes. Thank you.